project set in the Industry 4.0. Imagine a worker and a robot collaborating, the cobot, collaborative robot. The human is assembling some pieces on a table. The robot is doing the same in another table, and every more or less 50 seconds, 1 minute, they join together, they put these two subparts together. The man is, or the woman, is putting the piece in a container and they start over again for 8 hours a day. So, the goal of this project is to understand what is going to happen mentally to a worker collaborating with a robot when doing such a repetitive task all day long, every 5 days a week. So the goal of the project is to monitor the mental state or infer the mental state of the worker through several steps. And in my work, I'm focusing on what we can understand by using a webcam from the face, and specifically balance, arousal, and dominance, inferred from facial expressions, and how we can use it to drive the behavior of the robot and an avatar. The avatar is something like the avatar of the robot. So together with the robot, it is working. You have a tablet where a small avatar can do something and can say something, can be animated and say something to the worker. The idea is that a person is normally working happily in the flow. When something is wrong, stress, anxiety, distraction, the avatar and the robot can trigger an intervention to try to lead the worker back in the optimal state. So the theory developed by my colleagues, the psychologists, say, okay, we have 3 dimensions, 3 curves that in time they are smoothly moving, more arousal, less arousal. When I see that all of the 3 have a very strong value, I am in, if this is a 3-dimensional space, I divide this space in 8 zones. When I am in one of these zones, I assume that either it's perfectly good, like I'm in a flow zone, I don't do anything, but if I am in, for example, in the anxiety zone, I want to activate a behavior of the avatar, and maybe I want to slow down the robot. This is the dream, and this the basic idea is very simple. Now we switch into the engineering part. These 3 signals are very smooth. They cover the range, normalized from 0 to 1. The distribution is normal, and we also assume that when somebody is not having a facial expression, I mean is neutral, it means no facial muscle activation, all the values are perfectly centered into 0.5. None of them is true. So, after plotting the first data, the tragedy started. This is a plot of the 3 dimensions. I don't know if you see there are small vertical lines, and all of these lines, they represent one of the moments when the robot and the man and the human are joining the pieces. And this is a moment where the operator, the worker, is pushing a pedal in order to ask the robot to release the gripper and give the piece back. This is repeated this is a short interaction of 30 minutes. And so, the signal is jittery. It doesn't cover the full range. The distribution is not normal. There is a right skew. And we noticed with several tests on 16, 18 people, when you make neutral facial expressions, the outcome is never 0.5. Somebody is centered at 0.4, somebody is 0.65. So we cannot assume that this is a simplistic model based on using a threshold to understand if a signal is high or low. This is simply not working. And also, we were assuming that when an emotional state happens, the 3 signals are activated in the very same moment. Also, this was not true. So, in the next two slides, I'm using the numbering that is also in the paper to show you briefly an overview of what we did in order to have a useful system. Because the first version of the system essentially was an avatar that every 2-3 minutes was repeating, you look tired, maybe you want to take a break. You look tired, maybe you want to take a break, and so on. And then I asked my colleague to try it, and the behavior was different. So we started to really crunch the data, and we realized that first, a lot of jittery data, we need a bit of pre-filtering. So simply, the median of the last 5 samples is useful enough, so the median of 1 second of signal is good enough in order to limit the jumping of the signal. Calibration. At the beginning of every session, which means every morning, every user has to go to a passport picture. So please, no facial expression, watch the camera for 10 seconds, we record the data, and we use the median on the PAD values, these 3 medians, will be the key values to center all the data in future computation. And this is something you have to repeat every morning, because you just grow up the beard, you wear the glasses, you put lipstick, and these values will be changing. So the system needs to be recalibrated every day, essentially. Then, overcoming skewness. We don't have a threshold that is symmetric. We need to compute positive and negative thresholds. So, after calibration, the new PAD signals come from the camera and from a neural model. And we calibrated on the recordings of 20 subjects, more or less. After centering the data on the median of the calibration, we compute the root mean squared error separately for positive and negative values, because the ranges, I mean, the distribution is not normal, so you need to separate the 2 halves. Next step. We were assuming that when something happened, a moment of anxiety, the 3 signals are going up or down simultaneously. No, they have different delays. So instead of watching at each, 5 times per second is our sampling rate, instead of watching at each moment in time, each sampling, if these signals are high, we have to watch back in time if for a certain amount of time all the 3 signals, not at the same time, but anywhere in this time window, were in a high value. And after experimenting a lot, we decided that this time window can be from 30 seconds to 1 minute. And this is in concordance to some theory in psychology. Final step, synchronize with the working task. Our task, we noticed that every 1 minute, more or less, when the operator and the robot were synchronizing, and the operator needed to push the pedal in order to trigger the gripper of the robot, this was a moment of high concentration. I will not allow the avatar or the robot to intervene in this moment. We don't want it, cannot happen. So we decided this is a moment where we have to do the work, do his very delicate task of watching down, here is the pedal, click. Only then we start the computation by analyzing all the time that was before the click, which is from now until the previous interaction moment, more or less 50 seconds. So this time range is in the 30 seconds, 1 minute. It is good for us, it was a perfect match, but do not assume that at any moment you can activate an avatar. This might be annoying and distracting, while it's better if you observe and tailor the solution according to your specific task. Summary of conclusions. The PAD social signals, at least from one camera, cannot be used as they are. They are too noisy and jittery. A user per person calibration, maybe on a daily basis, is mandatory. You need to have a baseline, some measurements, in order to tune your thresholds on when to activate or not. And then a global controller. If we just use the root mean squared error of the thresholds, the avatar will be activating too often. We want to give the final operator, supervising the experiments, a nod to regulate the sensitivity of the experiment. With this multiplier, we move the thresholds away from the center in order to make the system intervening less. Or we can tune it down so the system, the avatar, will speak more often. But this has to be left in the hand of somebody there. Otherwise, the avatar can be either too annoying or do not speak at all in 8 hours, and so be completely useless. And as I said before, you need to watch the task and decide when and when not the system should do an intervention. Yeah, that's it.
Thank you very much.